Hey, period 5, Mr. Cash. It's April the 2nd, and I just got an email from the superintendent that we are done for the year. I am so stinking bummed. I'm just so bummed. Anyway, the only thing I know to do is just to carry on with our learning here. I'm getting paid, so I'm going to be working for the next couple months, and you're going to be getting a grade. So hopefully you're going to be learning. So here we go. A couple days ago, I put an announcement in Canvas asking any of you to create an example of a two-sample proportion hypothesis test. And our very own Isabella came up with a good one here. So what you see here is her scenario she created, and it is very, very timely. I think we all can relate to what's going on in this scenario here. So here's an example for section 10.1 in our textbook where we're dealing with proportions, and this is two samples. So here's a good question here. Will vaping or smoking increase the risk of catching the coronavirus? The CDC recommends that vapors and smokers should stop smoking, and their risk for COVID-19 will decrease. So we want to know, is that a valid recommendation? Does it really matter if you smoke or vape? Let's find out. So at a large U.S. college, an SRS of 200 men and women who smoke and 95 who don't smoke were sampled to see if they were more susceptible to catching the disease or not. It turned out that 53 of this 200, okay, there was our first proportion, and 11 of the 95 got the coronavirus. Okay, so notice I have hats here because these are samples. Okay, P hat 1, P hat 2. So P hat 1 we're going to call the smokers and vapors. P hat 2 are the non-smokers, vapors. And what we're really concerned about, what we're really trying to test, is what is about the true proportion of all vapors and smokers, and what about the true proportion of all those who don't. And the typical alpha value, the significance value, alpha here, would be 5%. And if 1 is not given to you, use 5% as kind of a default. Okay, so we want to see if the difference is statistically significant or not. So here we go with a state plan to conclude. State. We want to test if the proportion of smokers who contract COVID-19 are higher, okay, than those who don't. And the reason why we're choosing higher is not because this proportion is bigger than that one, the numbers, okay? So we don't state our hypotheses based upon the numbers in the problem, but based upon the wording of the question, okay? So this is hinting that smokers and vapors would have a higher proportion. So the wording of the question is leading us to believe that we want to test to see if it would be higher. Okay, so once again, I'm going to choose P1 for the true proportion of the smokers and vapors, and P2 as the true proportion of non-smokers. Once again, in your hypotheses, you're never going to use P hat. You're never going to use X bar. Those are samples. We're testing population proportions in this case. So our null hypothesis, another way to write this is that P1 would be equal to P2. Okay, so this would say that there is no difference at all. When you subtract two numbers and you get a difference of 0, you're pretty much saying that the two proportions are the same. So that's our null hypothesis. Our alternative hypothesis is that the true proportion of smokers is higher than those who don't. Okay, and here's another way of writing it as well. Okay, so on to the yucky stuff here, the parts that we all don't like to show and do. So remember in our plan, we have 3 different things we have to check. Randomness. In the wording of the question, it says that it was an SRS. 10% rule. Okay, In the problem, it was stated that it was from a large university, And it's safe to say, now notice we have two different sample sizes. We have sample size 1 and we have sample size 2. Okay, now both of them, when you do 10 times the sample, you get 2,000. 10 times 95 is 950. Obviously, you only have to check the largest of the two, but you have to make sure you check that the larger sample is at least 10 times that the population is 10 times the larger sample. And don't forget about the third condition. It's called large counts. So let's go on to the next one here. The third condition here in our state plan, we haven't even done anything yet. We're just checking the conditions. So we have our first sample, our second sample. I rounded these p-hats to the nearest hundredth just for ease of use here because I'm going to eventually be using my calculator anyway. Notice since we have two different proportions, here's my p-hat 1, and this is 1 minus p-hat 1. So in chapter 9 and even in chapter 8, when we check this condition, we only had to do it with one sample. N times p has to be greater than n times p has to be greater than 10, and n times 1 minus p had to be greater than 10. But that's only with one sample. We have a second sample here, so we not only have to check the first sample, but also the second one as well. So here is with our p-hat 2 and our sample 2. So just keep that in mind. You have to check the conditions for both samples. Extra tedious and long. All right, so state plan. We're on to doing here. Do, third step. Now, here is the test statistic formula. In your textbook, it's also in the formula sheets. You do not have to memorize this. It is the most tedious thing in the entire book. But I'm going to write it all out here. So this formula here, once again, you don't have to memorize it. So this is the difference of the two p-hats. That's the easy part. Now the denominator here, this is the sample size of the first sample, second sample. Okay, here's our P sub C. Now this is brand new to most of you. There's something called a pooled P. Okay, and you only use a pooled P when you're doing a hypothesis test. Okay, you do not pool the P if you're doing a confidence interval. A confidence interval, no pooled P, yes, because your graphing calculator will ask you pooled P, yes or no. And simply put, there's a good reason for this. I'm not going to explain it now. But if you do a hypothesis test, you pool the P. This is how you do it by hand. If you took both samples and you invited them to a pool party, okay, there would be 200 vapors and smokers. There would be 95 non-smokers and vapors. That would be a grand total of 295 people in one pool, okay? Now, if we took out the people that only tested positive, that would be 53 and 11. So we have a grand total of 64 people that tested positive out of the whole pool, okay? So when you pool the P, a lot of students think that they have to add these two fractions. This is p-hat 1, p-hat 2. This is no. You don't add the fractions. You don't need a common denominator. Literally think of it as a pool party. You're inviting all of these 200 people. You're putting all these 95 people and you're putting them in the same pool. And then out of each proportion, there's a grand total of 64 people that tested positive. That gives us a pooled p-value of 0.22. All right. Now, the 0.22, I put that there. 1 minus 0.22 is 0.78. What I'm doing is I'm showing you the numbers from here over here, okay? It's the same numbers here and here as well, okay? And those of you taking the AP Stat test, if you're able to construct this, if they do give you a free response question and you're able to set this baby up without being in a classroom and getting teaching, I think it would really make a good impression that you've done your homework. So I don't know if they're going to choose a 2-sample P, but it's definitely within the scope of study. So let's be ready. Now, when you crunch all this out, and I put the 0.22 here, we get this in the denominator. If I divide these two numbers here, I get 2.9. Now, 2.9 is called the test statistic. I go to my Z table. If I go to my Z table and I look up 2.9, and I look at the Z table that you used all the way in Chapter 2, way back in September in this class, it says that the p-value, this is capital P, this is probability, not to be confused with pooled P, P hat 1, P hat 2. This is probability, not proportion, okay? So this is the probability. It says that it's 99%. However, that is the area to the left of the z-score. We want the area up here. How do we know that we want the area up there? Let's go back to our null hypothesis. We are choosing a greater than scenario. So since it's a greater than, we're going to be taking the area in the upper tail. So if you do 1 minus all this orange stuff, you end up getting this p-value. I'm ready to make a conclusion. Now, this decimal is exactly, I mean not exactly, it is a lot less than 0.05, which is our alpha value. So we are going to reject the null. We're going to reject the null, which means we are rejecting this because the p-value is less than 5%, which means that we have enough evidence to say that smoking does and vaping does make a difference. Now, in conclusion, all this stuff here you can set up by hand. Now, I calculated it by hand because I wanted to show you where all the numbers come from. But if you use this chart that I put on Canvas just a couple days ago, it's a handy-dandy chart. This is what you're going to use here. You're going to go to Stat Test, choose item number 6. You're going to give it 53 people out of the 200. That is the first proportion. And then there's 11 people who tested positive out of the 95 that did not smoke or vape. And then you choose, in this case, we're going to choose that the first proportion is greater than. So we're going to choose this one here, and it's going to spit out this decimal, which is very, very close to this one, okay? It would be the same conclusion, that this is less than 5%. You're going to reject null. And then, of course, when you reject the null, state your conclusion in context, which means that there's significant evidence that smoking and vaping does make a difference because you rejected this, which means that you accept this. So this is statistically significant because the p-value is a lot less than alpha.